So, hello everyone again. This is lecture 1 part 3 of wave optics. In the last lecture we completed with the introduction part of wave optics. In this lecture we will start with Huygens principle. So, I am Sameer Lavankar. Let us begin our discussion. So, the course outline for you. So, the first point, that is introduction part of wave optics, difference of wave optics and ray optics, a little bit about bending up of light when the dimensions of the obstacle is intact or insimilar with the wavelength of light is being studied in this part of the chapter. Today we will be starting with the Huygens principle. Let us move on to the Huygens principle without wasting any time. So, Huygens principle is the name of the Huygens is the name of the scientist, and principle is the principle he inculcated about the wave theory of light. So, let us first define a wavefront. So, an important concept being talked about in the complete lecture series will be about wavefront. So, you need to understand this new word here, not a very difficult word, but sometimes explanation of this is a little tedious. So, please look out to the definition of wavefront first. So, let us first define a wavefront. When we drop a small stone on a calm pool of water, waves spread out from the point of impact. So, this is the diagram showing you that waves coming out of a calm water. So, this is nothing but the ripples being formed in a circular fashion when the stone or when a small stone is being put into the water. The assumption is that the water should be calm. So, when you drop a small stone on a calm pool of water, waves spread out from the point of impact. So, this here is the point of impact. Let me write here for more clarity. So, this is point of impact. So, this is the point of impact. Every point on the surface starts oscillating with time, every point on the surface. So, this is the complete surface being talked about here. So, everything on the surface starts oscillating as in the movement, the displacement. Let us say this is the original calm pool of water. This is the calm pool of water. So, if with time I try to make a diagram, if the movement is like this or if the movement is like this, so this at any point t, this is the highest displacement which is being shown at that particular point we are talking about, at any point on the surface. So, every point on the surface starts oscillating with time. At any instant, a photograph of the surface would show circular rings on which the disturbance is maximum. So, circular rings, just to iterate to you. So, these are the circular rings being drawn here. So, these circular rings are nothing but the rings or the positions or the points on the surface or the locus of the points on the surface which have a maximum displacement. So, maximum it is local maximum, because the portion just near that circular ring will have a depression, and just beside that ring will be another circular ring. So, this will be local maximum. So, these points of local maximum, these locus of points of local maximum will have a will go in same phase, and hence will have a same displacement, because the displacement is maximum along that local maximum, hence circular rings are being viewed. So, every point on the surface starts oscillating with time. At any instant, a photograph of the surface would show circular rings on which the disturbance is maximum. All points on such a circle are oscillating in phase as in they are oscillating with the same time lag. So, all points on such a circle are oscillating in phase because they are at the same distance from the source as in this point of impact. So, point of impact is nothing but the source. Let me write it here only. So, this is nothing but the source here. So, all points on such a circle are oscillating in phase because they are at the same distance from the source. Such a locus of points which oscillate in phase is called a wavefront. So, this is nothing but the typical explanation of what is a wavefront. So, such a locus of points which oscillate in phase. So, this circular ring, any circular ring which we take into contact is nothing but a wavefront. So, this is also a wavefront, this is also a wavefront, this is also a wavefront. Anything which is far apart, let us say 5 to 10 centimeters far apart, which is not even visible, which is oscillating in phase, is also a wavefront. So, moving on. So, this was the typical definition of wavefront. Typical diagrams of wavefront will be explained to you in subsequent slides. For now, such a locus of points which oscillate in phase is called as a wavefront. Thus, a wavefront is defined as a surface of constant phase. So, constant phase, why it is constant phase? Because they are at the same distance from the source. So, any point which is at the same distance from the source will be oscillating in phase, and hence the locus of such points is nothing but a wavefront. So, this was this was a slide just to explain you the basic definition of wavefront. Let us move on. So, this is also on the right hand side, you can also see a typical diagram of wavefront only. So, this is nothing but the source, and these concentric circles are nothing but different wavefronts. So, as the time goes on, the value of that circle, the radius of the circle increases. So, if this is at t is equal to 0, this will be at t is equal to t1, or let us say to make it more clear, this is at t is equal to t1, this is at t is equal to t2, this is at t is equal to t3. Here t1 is less than t2 is less than t3, that is t3 is the at the maximum time, which is far away from the surface as compared to the first wavefront. So, just it was just the typical model of above diagram only, when we view it from the above, and when we view it only to show the circular rings. So, the speed with which the wavefront moves outward from the source is called the speed of the wave. It's quite evident. So, this diagram or this vector shows you the direction of the movement of the wave, and hence this is the speed of the wave. So, the speed with which the wavefront moves outward from the source is called the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront. So, perpendicular wavefront as in this is the direction, this is the wavefront here. So, this is the perpendicular to the wavefront. So, the energy of the wave travels in a direction perpendicular to the wavefront. If we have a point source, so this is a point source only. If you have a point source emitting waves uniformly in all directions, so as you can see that the waves are being emitted in all directions only, hence it is uniform. So, if we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude and vibrate in the same phase are spheres. So, when we see the 3D diagram of it is nothing but a sphere, same are spheres, and we have what is known as a spherical wave as shown in the below figure. So, this is the below figure which is being talked about here. So, everything which is moving analogous or which is moving uniformly in all directions at a point at a radius which is intact, the amplitude will be maximum, or amplitude and the oscillation will be in phase. If it is in phase, then the radius or the periphery of that sphere is being talked about here. So, that periphery of the sphere is being nothing but a wavefront. So, that is the only concept being talked about in the second point. So, what we have, just to iterate to you again. So, the energy of the wave travels in a direction perpendicular to the wavefront. If we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude as in the displacement from the if I make a xy plot here. So, not a xy plot, let time and y plot. So, this is a maximum displacement. So, nothing but these all points are nothing but the amplitude only. So, if the amplitude of all the points at a distance at a constant distance r from the source will have the same amplitude, and this is the only point being talked about here. So, if we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude and vibrate in the same phase are spheres, and we have what is known as a spherical wave as shown in the below figure. So, this is the only concept being talked about here. Moving on. So, at a large distance from the source, a small portion of the sphere can be considered as a plane, and what we have what is known as a plane wave. So, this is being just to iterate to you. Let us say I make a very big sphere. So, any point which is if the volume or if the radius of this sphere is very large, then if I take a very small portion out of that sphere, on the visibility to a naked eye or when we visible it, then that rectangular portion on that sphere can be located or can be assumed to be a plane, a rectangular plane or rectangular sheet. That is why the propagation is called as plane wave propagation. Just to explain to you more, like let us say if I use a hand only. So, let us say if I make a small circle, then the, as you can see, the curvature is very large. If I keep on increasing, the radius to make it a given bigger sphere, then as you can see the curvature is getting reduced. At one point, if I keep on increasing the radius, at one point will come when the portion of this curvature will be approximately equal to the rectangular wave or rectangular sheet. So, if I take this, if I cut out this portion from that sphere, so this is only the portion being talked about here. So, at a large distance from the source, a small portion of the sphere, so this is the small portion we are being talking about. If this is a complete sphere, can be considered as a plane. So, this is nothing but that plane being talked about here, and these are nothing but different. So, let us say if this is a sphere, this is a sphere, this is a sphere. So, these were the 3 rectangular sheets. So, these are 3 rectangular sheets, 1 2 3 1 2 3. So, these are these 3 rectangular sheets only and only if the radius is very large. Moving on. So, this was the concept we talked about here, and this is what we know as a plane wave. So, plane wave is nothing but a wave passing through a rectangular sheet in a straight line. So, now if we know the shape of the wavefront at t is equal to 0, then Huygens principle allow us to determine the shape of the wavefront at a later time tau. So, let us say this is the wavefront which we know at some t is equal to 0, then using the Huygens principle we will get to know what will be the wavefront at some t is equal to tau. So, to find out this wavefront, is nothing but the procedure which we need to adopt using the explanation of Huygens principle. So, let us explain this, and let me explain this last point only in the subsequent slides front. So, please look over here carefully, sometimes this thing can be a little tedious. So, thus Huygens principle is essentially a geometrical construction. So, just to explain the wavefront, it is nothing but geometrical construction, so that some of the circles are being made and tangents are being drawn, then we can find out the next wavefront at some time t is equal to tau. So, thus Huygens principle is essentially a geometrical construction which, given the shape of the wavefront at any time, allows us to determine the shape of the wavefront at a later time. So, this is nothing but the last concept only, that if the value or if the shape of the wavefront is being known at some time t is equal to 0, then the shape of the wavefront at some time t is equal to tau can be known by using the concept of Huygens principle and some geometrical construction. So, let us move on. So, let us consider a diverging wave, diverging as in coming from a source and diverging apart. So, moving apart, converging as in coming from different sources and converging at a point or going through a point, diverging as in a source is given and everything diverges apart from it. So, let us consider a diverging wave and let f1 f2 represent a portion of the spherical wavefront at t is equal to 0. So, this f1 f2 is nothing but a portion of the spherical wave. So, this is nothing but wavefront, let me write it here. So, this is nothing but wavefront at t is equal to 0. So, now let us consider diverging wave and let f1 f2 represent a portion of the spherical wavefront at t is equal to 0. So, completely, so it would be have like this, and it would be of a 3D shape, but for now we are taking a 2D planar shape that also as an arc of a circle. So, now according to the Huygens principle, each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating as in producing from that source, from these points spread out in all directions with the speed of the wave. So, let me explain this again bit by bit. So, what does Huygens principle say is each point of the wavefront. So, this is the complete wavefront. So, if I take any points on this wavefront, let me denote it by green point here. So, if I take any point on this wavefront, so there can be infinite points on this wavefront, is the source of a secondary disturbance. So, the primary disturbance was being told when the let us say if I take the example of primary disturbance. So, if I take an example of a stone being put in a calm pool of water, then that throwing up of stone when it hits the water, then that is nothing but a primary disturbance. What it says is that there is, because of this movement of the wavefront, there is a secondary disturbance being talked about in the in that wavefront, near that wavefront. So, what it says is this portion, these green points are nothing but a source of secondary disturbances. This is the principle of Huygens, this is the Huygens principle, secondary disturbances. So, what these secondary disturbances do? They also emanate wave. So, these wavelets emanating from these points spread out in all directions with the speed of the wave. So, these blue lines which you can see are nothing but the spheres emanating from that secondary disturbances only. So, when we try to find out the tangents of these waves, we will get the next wavefront, and this is nothing but a small concept of Huygens principle. So, just to iterate to you whatever is written here. So, these wavelets emanating from the wavefront are usually referred to as secondary wavelets. So, this is nothing but these blue lines are nothing but secondary wavelets, are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres. So, if a common, so at point A dash, so just to remove this. So, if I try to find out these points, so let us say this point be 1, let this point be 2, let this point be 3, and if I try to make a tangent, if I, first of all these are the secondary, so these blue lines are nothing but secondary waves, secondary, let me write secondary wavelets. So, these are nothing but secondary wavelets. Now, if I try to make a tangent from these from the secondary wavelets, so this is the thing which we will get, and this thing which we will get is nothing but the wavefront at some time t is equal to tau. So, these wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at some later time. So, this was nothing but the concept of Huygens principle, hence we got to know about this wavefront. But now question arises, as it was shown that the secondary disturbance is a complete sphere again. If it is a complete sphere again, and if we draw a tangent going towards the forward, what about these blue lines? What about these secondary disturbances? It also comes back. Then at some later time t is equal to tau, there is two wavefronts being formed, one at the forward position, one at the below position. So, what about these? What about this? What about this wavefront? So, that was one of the difficulty, or that was one of the, let us say, rejections being analyzed for Huygens principle. We will got to know about this concept also. Let us move on to the next slide for now. Thus, if we wish to determine the shape of the wavefront at t is equal to tau, we draw spheres of radius v into tau. Quite evident, as we know that distance is equal to speed into time. If the distance being talked about is this, let us say this is the radius, then this radius is equal to speed. Speed is nothing but the velocity v, and time is here tau. So, therefore, this radius is v into tau. From each point on the spherical wavefront, where v represents the speed of the waves in the medium. If we now draw a common tangent to all these spheres, we obtain the new position of the wavefront at t is equal to tau. The new wavefront shown as G1, G2 is again spherical with point O as the center. So, this G1, G2, this is G1, this is G2, this is again spherical as in this is the only 2D shape. At any point this will be same only. So, when we will got to know that if this is a small circle, if we got to know, if we make a small sphere out of each of this, and we got to know the secondary disturbances, and got to know a tangent, we got to make a tangent out of the secondary disturbances, and then we will get to know a new wavefront which is again a spherical shape only. So, this was being talked about. So, the new wavefront shown as G1, G2 is again spherical with point O as the center, point will be O only as the center. So, let me stop the complete concept here only. In the next lecture, we will get to know the shortcoming. The shortcoming is nothing but that only, that the sphere is being made, the forward wavefront is okay, it is quite nice, but a wavefront being the secondary disturbance also makes a wavefront in the backward position. What about this D1, D2? Do we take it into consideration? Do we neglect it? What was the explanation talked about D1, D2 by Huygens? We will get to know this in subsequent lectures. For now, what we got to know is what is the definition of a wavefront, how are the wavefronts being formed. One of the examples of wavefront we got to know about what. So, first of all, the locus is nothing but the wavefront having the same amplitude, they are in phase. Then we got to know how a wavefront can be created at some t is equal to tau if we know the wavefront at t is equal to 0. In the next slide, in the next lecture, we will get to know the shortcomings of Huygens principle. For now, let me conclude this lecture here only. So, the course progress for you at the end of the lecture 1, we started with the introduction part. We got to know the ray optics, linear propagation of light, then we got to know about the wave theory of light, the propagation, the experiments performed using wave theory of light, and finally, in today's lecture, we are in Huygens principle. In the next lecture, I will tell you about the shortcomings of Huygens principle, and then we will move to third point, that is refraction and reflection of plane waves using Huygens principle, and then finally different concepts of wave optics will be dealt with clearly. For now, thank you.